linear discrimination models try to find a separating hyperplane defined by a linear combination of the feature values. They classify by checking on which side of the hyperplane a data point is. And if the weights in the linear combination are chosen to be very large, the model is overfit because even small changes in a data point may lead to drastic changes in the discriminator. And that's where regularization plays an important role. Regularization for linear models works by reducing the weights in the model to reduce the overfit. And that's especially useful when the number of features is much larger than the number of data points, or for example, when the features are highly correlated. And the general approach is that you use a penalty term in the objective function. So in addition to what we normally have in linear models by looking at the loss function, you add this extra term where RW is some sort of a regularization term, and I give some examples in just a moment. It should be thought of as a penalty on the weights. The higher the weights are, the higher this penalty is. And this lambda is a parameter that you choose for yourself, and that's the strength of the regularization. So the smaller the lambda is, the less you are paying attention to the model size, to the model complexity, and the higher it is, the more important it is in the optimization, and the more you are going to aim for a smaller model. So here are three of the most commonly used regularization functions for linear models. The first one is the L1 regularization. This is also known as lasso regularization. And the function in this case is just R applied to vector W is simply the one norm of W, or in other words, is the sum of the absolute values of all the entries in vector W. This form of regularization tends to push many coefficients to zero, so that's going to lead to a sparse model. And that's especially useful if you want to do feature selection with a linear model. Here is a second option, that's an L2 regularization. This is also known as ridge regularization, and in this case the regularization term is simply just the 2 norm of W divided by 2 for reasons that have to do with partial derivatives. So in other words, this is just 1 over 2 sum of, and then you take the square of all the entries in the weight vector. This sort of regularization, in contrast to a lasso regularization, tends to keep all features, but is going to shrink their coefficients. And finally, the third one is the so-called elastic net, which is a combination of L1 and L2. So in this case, there are in fact two different regularization terms, one which is the 1 norm and the other one which is the 2 norm, each one of them with two independent parameters. And this is in fact commonly used for high dimensional data.